text box. So last time we started, but we didn't finish section 15.5 on arithmetic series. And so an arithmetic series is a sum of whose terms are terms from an arithmetic sequence. The summation notation involves the summation symbol, which is just a sigma, which means to add every number from your lower limit to your upper limit, where you calculate each of those numbers by whatever formula is given within the summation. And in statistics, they use this set notation, if you remember, where they sum over members of a set. And many times they don't, well, they never hardly ever write what the set is. It's understood. And so we did some examples where we expanded the terms of a series using sigma notation. Okay, and then we looked at if things were arithmetic or not. Okay, so I think that was about where we ended last time, was I think on problem number 24. Okay, so, and this is it right now. So let's start with the new stuff. And so, oh, and recall that in order for you to get credit, you need to either email me or text me your pictures of the lecture notes for today by Monday at midnight. And so they have to be received by me before Monday at midnight to get credit for the, yes. Okay. And so let me give you a formula for the sum of the first n terms, well, of n terms, let's say, of an arithmetic series. And so, Carl Friedrich Gauss, when he was 10 years old, he was in class, I guess, I don't know, second or third grade, and his teacher, I guess, wanted to keep his little children occupied while he did something else. And so he gave the following problem on the board: add 1 plus 2 plus 3 plus all the way up to 100. And thinking that this would take these children all day to do, well, after he wrote down the problem on the board, right when he turned, Carl Friedrich Gauss all of a sudden jumped up and, was waving his hand saying, "I know what it is." And so he said, well, the sum is 5,050. So let's see how he did that. And so if I look here at 1 plus 2 plus 3 plus, I don't know, 98, 99, 100. Well, let's look at the same sum, but let's look at 100 plus 99 plus 98 plus. So just writing the same sum, but instead of going in increasing order, let's go from decreasing. So let's go from top to bottom rather than bottom to top. And so let's add these. Well, s plus s is 2s. 100 plus 1 is 101. 2 plus 99 is 101. 3 plus 98 is 101. 98 plus dot dot dot. 98 plus 3 is 101. 99 plus 2 is 101. 100 plus 1 is 101. So notice that all these numbers are 101. And there are 1, 2, 3, dot dot dot, 100 of these. And so we get that 2 times the sum that we want is 10,100. So therefore, oops, if I divide both sides by 2, I get that the sum that I wanted to calculate is 5,050. And so that is how Carl Friedrich Gauss determined what that sum is. And of course, being 10 years old, he had nothing to do over the weekend, so he basically did all that we're doing in chapter 15 over the weekend. And so let's derive the general formula for the sum. And so the sum of an arithmetic sequence, let's say from k equaling 1 to n. Well, every arithmetic sequence looks like a1 plus k minus 1d. Well, we get that the sum is equal to, well, n over 2 times a1 plus an. So you just add up the first term and the last term, 1 plus 100, and then multiply by how many terms there are? Well, 100, and then divide by 2. Oh, okay. So that's called Friedrich Gauss's formula. Now, of course, I can replace a sub n by the formula we have for the general term, a1 plus n minus 1d. And so if I do that, I also get the formula in the form n over 2 times, well, I have an a1 plus another a1, so that's 2a1 plus n minus 1d. And so that is the formula for the general term. So I guess I can derive it. So let me do that. And so I have here, well, let's show this. Oops, sorry. So let's derive this. And so I'll just show that this last part here is true. So I'll just show this. Obviously, the first formula I have is the same, so I just need to show one of them. So first, let's do this by induction. So let's do the initial case. Well, let's show that this is true for the case n equals 1. And so let's replace n here by 1. So the sum, k equaling 1 to 1, sorry, the sum, k equaling 1 to 1, of a1 plus k minus 1d, well, that's equal to, replace k here by 1, that's a1 plus 1 minus 1d, which is a1. And we also have well, replace n by 1, And so 1 over 2 times 2a1 plus 1 minus 1d, well, that's equal to 1/2. Well, 1 minus 1 is 0 times d is 0 plus 2a1 is 2a1. 2's cancel, so you get a1. So therefore, I've shown that the sum k equaling 1 to n of a1 plus k minus 1d is equal to n over 2, 2a1 plus n minus 1d when n is equal to 1. And that's what I wanted to show for the initial case. And so let's do the induction case. The induction step. And so suppose that the sum k equaling 1 to n of a1 plus k minus 1d is equal to n over 2 times 2a1 plus n minus 1d. Then I want to show that this holds when I replace n by n plus 1. And so then, well, let's replace n by n plus 1. Let's see if this holds. a1 k minus 1d is equal to, well, this is equal to the first n terms plus the last term. So last term would be a1 plus n plus 1 minus 1d. Well, by the induction step, I know that this is equal to n over 2 times 2a1 plus n minus 1d plus this last one, which is a1. The 1's cancel, plus nd. Let's simplify this. And so let's multiply the n over 2 inside the parentheses. So I get n over 2 times 2a1 plus n over 2 times n minus 1d plus a1 plus nd. So the 2's cancel. And so I get n a1. And let me write the a1 next to it, plus a1 just grouping those terms together, plus n over 2 n minus 1d plus nd. Let me actually write this as n over 2 times 2d, because the 2's will cancel, so I haven't changed anything. So let me factor out first an n in this first term, and so that's n times, let's factor out an a1, and so that becomes n plus 1 a1. Let's factor out from this last n over 2 d. And so if I take out the n over 2d, what remains of the first term is n minus 1. What remains of this last term is, well, 2. Okay. And so this becomes, well, I'll write this as n plus 1 over 2 times 2a1 maybe I should have multiplied out that whole thing so I can write it as n plus 1 over 2. Yeah, I guess I should have. Okay, so this becomes plus n over 2 times, well, n minus 1 plus 2 is the same as n plus 1 d. And so this is equal to n plus 1 over 2 times 2a1 this becomes, well, I have an n plus 1 over 2 times nd. And so this becomes n plus 1 over 2 all times, so I can factor out the n plus 1 over 2's, which are in common, 2a1 plus nd. Now let me rewrite this finally as 2a1 plus. Let me rewrite n as n plus 1 minus 1. So I've just added and subtracted 1, so I've done nothing. But that's what we want to show. Therefore, the sum k equaling 1 to n of a1 plus kd equaling n over 2 2a1 plus n minus 1d. This implies that the same formula works when I replace this n by n plus 1. So this implies that k equaling 1 to n plus 1, a1 plus, oops, that was the error, plus k minus 1d is equal to n plus 1 over 2, 2a1 plus n plus 1 minus 1d. So this says that if I assume that the formula works for n, then the formula works when I replace n by n plus 1. And so I've shown the induction step. So therefore, by the principle of mathematical induction, the sum we have that for all natural numbers n, the following formula works. The sum k equaling 1 to n of a1 plus k minus 1d is equal to n over 2 2a1 plus n minus 1d. And so I am done. Okay, so let's do some examples. Let's say on page 664, let's do problem number, let's say 25. Two plus 4 plus 6 plus 8 plus 10 dot dot dot. In exercises 25 through 30, find the sum of the first 100 terms of the arithmetic series whose first few terms are given. And so let's do that. So we know the formula for the first n, sum of the first n terms of arithmetic series. Let me just denote the sum of the first n terms by the following notation, s of n. So that's just equal to n over 2, 2a1 plus, now I can either use the first formula I gave you, n over 2, a1 plus an, or this second formula. Since I don't know the last term, I'll use this formula. So let's find the sum of the first 100 terms. Well, what's n? Well, 100, because I'm adding the first 100 terms. 2 times, well, the first term. Well, the first term is a 2. Plus, well, how many terms are there? 100. Times, well, what is the common difference? Well, I keep adding 2 to get to the next term. And so let's find this. So this is 50 times 4 plus 99 times 2. And so 50 times 4 plus 198. So 50 times 202. Which should be 10,100. And so the sum of the first 100 even numbers is 10,100. Okay. Let me do, let's say 26, 28. How about 29? Let's do problem 29. 25 plus 21 plus 17 plus 13, etc. So let's find the sum of the first 100 terms. Again, we know what the formula is of the sum of the first n terms of an arithmetic series. And so the sum is either given by n over 2, a1 plus an, or 2a1 plus n minus 1d. And I'll use this formula since I know I do not know the last term. So since I don't know the last term, this is easier to use. And so let's find the sum of the first 100 terms. Well, I want 100 terms, so that's 100. N is 100. The first term is 25. There are 100 terms, so n is 100. The common difference is, well, negative 4, because I keep adding negative 4. And so this is equal to 50 times 50 plus 99 times negative 4. And so I get 50 times 50 minus 396. And so I get 50 times a negative 346, which is equal to a negative 17,300. And so if you added up the first 100 terms of that series, they would add up to a negative 17,300. Okay. Let me do problem number, let's say, 31. Two, 7, 12, all the way up to 102. In exercises 31 through 33, find the sum of the arithmetic series. Okay, so again, we're going to be using the same formula. Now, in this case, I know the last term, and so I'll use the following form, the first form, that the sum of the first n terms is n over 2 times a1 plus an. Okay, so now you notice that, well, I know the first term, I know last term. First term is 2, last term is 102, but unfortunately, I don't know n. So I'm going to have to figure out what n is. But we've done that before. We did that back in, I think, section 15.2 or 3 or something. 15.3, I guess. And so I know that the formula for the general term is just a sub n is a1 plus n minus 1d. Therefore, I can figure out n by just knowing n is the last position, is the position of the digit 102. So let's look at the term 102 and see what term that is in the sequence. Well, the first term was 2. I don't know n, that's what I'm trying to figure out. And the common difference, well, I'm always adding 5 to get to my next term. Let me subtract 2 from both sides. So 100 equals 5n minus 1. Let me divide both sides of my equation. Oops, sorry. Why 5? Oh, well, what's a common difference? How do I go from 2 to 7 to 12? What am I always adding? I'm always adding 5. And so notice I'm always adding 5. Okay? Is that clear? Okay, good. Okay, so let's divide both sides of my equation by 5. Oh, does that something else works for the geometric? So yes, this only works for arithmetic series and sequences. You're always adding the same amount. For geometric, you're always multiplying by the same amount. For other series, obviously you'll have some property, but it won't be the same as that. So this really only works for arithmetic, that you're always adding the same amount. Divide by 5. So n minus 1 is 20. Add 1. So n is 21. So now I can plug that in. So now I know what n is, and now I can figure out what this is. So the sum of the first 21 terms is, do a little more space, is n over 2 times a1. a1 in this case was 2. a2 in this an in this case, the very last term, was 102. So add the first term, I add the last term, then multiply by n and divide by 2. And so this is equal to 21 over 2 times 104, which is 21 times 52. And so you get 1,092. So if you add up these terms in this arithmetic sequence, in this arithmetic series, you get a total value of 1,092. Let me do another one. Let's say, so this was, I'm sorry, 31. Oh, yes. Where'd you get the 52? Oh, what I did is just, what's 102 divided, 104 divided by 2? So 104 divided by 2 was 52. I just canceled the 104 and the 2. Just because it was easier to multiply whole numbers rather than decimals. Is that clear? Okay. let, let me do 32. Let's do problem 33. Oops. 33. 28, 26, 24 to negative 6. So let's add up all those. And so again, I know the first term and I know the last term. So I'm going to use that formula to that their very first formula to find the sum of the first n terms arithmetic series. Unfortunately, just like in the last case, I don't know what n is. So in order to figure out n, I'll use the general term, the formula for the general term of an arithmetic sequence. So the last term is -6. And so to find the positional last term of the sequence, arithmetic sequence, all I have to do is figure out n. A1 is 28. And the common ratio, the common difference, sorry, is -2. And so let's multiply, I guess, the -2 inside the parentheses. So -6 equals 28 minus 2n plus 2. So -6 equals 30 minus 2n. Subtract 30 from both sides of my equation. And so -36 equals -2n. Divide by -2. So n is equal to 18. Okay, so good. I now know what n is. So I can figure out the sum of the arithmetic sequence, of this arithmetic series. And so n is 18. I can plug that into this formula. So 28 and -6. So 28 and -6. So the first term was 28. The last term was -6. And n in this case was 18. And so I get 18 divided by 2 is 9. Why 18? Oh, because there's 18 terms. Remember, the subscript just means how many terms are there. And so I found that n was 18. And so my notation is that to find the sum of the first n terms, in this case 18 terms, I just use the notation. That notation just means find the sum of those terms, the first 18 terms. 28 minus 6 is 22. Times 9 is 198. So the sum of the first 18 terms of the series was 198. Okay. Let's do problem number 34. This is very similar, which is, actually, I think we did this the other day, but yes, so I will be giving that in a few seconds when we do the word problems. So so I'll be giving you some problems in that, especially especially in the next section. Okay, so in exercises 34 through 36, find a formula for the sum of the first n terms of an arithmetic series whose first few terms are given. 1, 3, 5, 7. Okay, and so I want to find the formula for the sum of the first n terms. Well, I know that the formula is given as follows. And so let me do this. And so I just gave you the formula, I think yesterday, or no, it was the day before. I gave it to you on maybe on Wednesday. Oh no, it was on Tuesday. It was on Tuesday. Sorry, I gave you the formula on Tuesday saying, well, let's use this and and prove the formula using mathematical induction. So now we're actually going to derive it. So what's the sum of the first n terms of the first n odd terms? And so, close this thing. Oh, here it is. So let me close this. There. Well, the first term is 1. The common difference is, well, I'm always adding 2 to get to the next term. Let me multiply 2 inside the parentheses. Two times 1 is 2. 2 times n is 2n. 2 times 1 is 2. The 2's cancel. And so I get S sub n is n over 2 times 2n, and the n's and the 2's cancel. And so n squared. And so if you recall, on Tuesday, we proved the formula that if you add up the first n odd terms, that you just get n squared. And so we've actually shown that formula now, that if you add up these terms, you get the n squared. Let me do problem 35. -3 plus 0 plus 3 plus 6, etc. And so let's derive a formula for that, adding up the first n terms of this. And so the formula for the sum of the first n terms of an arithmetic series is 2n over 2 times the quantity 2a1 plus n minus 1d. Again, I don't know the last term, so I'll use this form of the formula. And so this is equal to n over 2 times 2. A1 is -3. D in this case, notice I'm always adding 3, so it's equal to 3. Why is it equal to n squared? Well, what's n times, so the 2's cancel, what's n times n? N squared. So I just multiply the two n's together to get n squared. Question? So when we did this on Tuesday, I just sort of said, well, that's sort of a, a formula, and I just gave it to you, and then we proved it using mathematical induction. Here, I'm actually deriving it. Oh, is this the answer? Yes. I'm sorry. I thought you said why. Is it the answer? Yes, it's the answer. I didn't box it. Haha. Yes, that is the answer. Okay, sorry about that. So this is equal to n over 2 times 2 times -3 is -6. Let me multiply the 3 inside the parentheses. So I get plus 3n minus 3. And so this is equal to n over 2 times 3n minus 9. And that is your formula. Maybe I'll put regular parentheses. Okay? And so that's how you can find the sum of the first n terms. So if I ask you what's negative 3 plus 0 plus 3 plus 6 plus dot dot dot, adding up n of these, adding up the first 1,000 terms, well, you just put 1,000 in for n in this formula, and out pops your answer. So once you have a formula like this, obviously it's very easy to find that in a sum for as many numbers as I ask you to. Okay, let me do problem number 37. S sub 12 equals 222. S 14 equals 301. In exercises 37 through 40, find a formula for S sub n, the sum of the first n terms of arithmetic series, using the given information. Okay, so this is actually going to be very similar to problems we did in the previous two sections, where we did this instead of for series, we did it for sequences. In fact, it'll be almost identical to what we did for arithmetic sequences. The formulas are very similar, so let us use the following formula. So note that S sub n is equal to n over 2 times, well, I'll know what n is in this case, but I won't know the nth term. Since I won't know the nth term, I'll use this formula. So notice, I guess I should note, if I use this formula, a1 plus an, and if I plugged in like 12 and 14, well, I get a12 and a14, so I'd have like 3 unknowns, and I really can't, I'll have 2 equations and 3 unknowns, so that's not going to work. So let's do it where I just have 2 equations and 2 unknowns. So in this case, I can actually, I'll know S14, I'll know N, but I won't know A1 and D in either of these cases. So I'll have 2 unknowns, but 2 equations from these 2 pieces of information. And so let's first plug in for N, 12. I don't know A1. I know N is 12. I don't know D. But I know that the sum of the first 12 numbers is 222. Okay, so that'll give me my first equation. And so let's simplify this. So 12 divided by 2 is 6. 2a1 plus, well, 12 minus 1 is 11d. Let me divide both sides of my equation by 2, because I'll make a slightly easier answer. And so I'll get 111 equals 3, 2a1 plus 11d. Let me multiply the 3 inside the parentheses. And so I'll get my first equation, 6a1 plus 33d equals 111. Let me call that r. So that's my first equation. Now for the second equation, I'll do the exact same thing. I'll plug in for n, 14. So the 14th number, the sum of the first 14 numbers is 301. I don't know A1. I know that there are 14 terms, and I don't know D. Just like in the previous case, I knew N, but I didn't know A1 nor D. Okay, so let's simplify this. 14 divided by 2 is 7. Oh, let's see, did I make a mistake? 301? 301, yes. The sum of the first, let me check if yeah, 301. So the sum of the first 14 term is 301. That was the given information. So the given information was that the sum of the first 14 terms is 301. Okay. Okay, so now 14 minus 1 is 13. Divide both sides of my equation by 7. And so I have 2A1 plus 13D equals 301 divided by 7 is 43. And so that'll give me my second equation, S. So I have two equations and two unknowns, and they're both linear equations, so I should be able to solve this. So why don't I take the S, I'll multiply it by 3, so that'll give me 6A1 plus 39D equals 129. Subtract from it R, which is minus 6A1 minus 33D equals minus 111. And so I'll just eliminate A1 and then solve for D. This is just a linear equation, a system of linear equations in two variables. The 6A1s cancel. 39 minus 33 is 6. 129 minus 111 is 18. Divide both sides of my equation, by 6. And so D is equal to 3. Let's figure out A1. Oh, I don't care. Let's see which easier equation. Let's use S. It says 2A1 plus 13D equals 43. So 2A1 plus 39 equals 43. Subtract 39 from both sides of my equation. And so I have that 2A1 is equal to 4. Divide both sides of my equation by 2. And so A1 is equal to 2. And so therefore, the general equation for the sum of the first n terms is just n over 2, 2A1 plus n minus 1D. And now we know each of these. And so A1 is 2, D is 3, Let me multiply 3 inside the parentheses. And so I get 4 plus 3n minus 3, which is equal to n over 2, and maybe I'll use the regular parentheses. 3n, 4 minus 3 is 1. And so if I add the first n terms of this series, it's just n over 2 times 3n plus 1. And that's my formula for the sum. Let's do maybe one more of these. Let's say 39. A1 is 5. S 14 is 549. So in this case, I know the first term, and I know the sum of the first 14 terms. So I can find, well, I can use either the first or second formula for the sum, but if I use the first formula, all that's going to give me is the value of the 14th term, and that really doesn't give me anything. So let's use the second form. So S sub n is equal to n over 2 times 2a1 plus n minus 1d. Okay. Let's plug in for n, 14. So the sum of the first 14 terms is 549. The first term is actually given. It's 5. So I'll plug that in. N is 14. The only thing I don't know is D, the common difference. And so I have one equation, but one unknown. So I should be able to figure that out. And so 14 divided by 2 is 7. 2 times 5 is 10. 14 minus 1 is 13. And so let me multiply 7 inside the parentheses. And so I get that 7 times 10, 70. 7 times 13, 91. D is equal to 549. Subtract 70 from both sides of my equation. And so 549 minus 70 is 400. Oops. $79. Let me divide both sides of my equation by 9. And so D, oops. Is equal to 479 over 9. And thank you. Thank you. Because I'm blind. Thank you. That would make life much easier if I actually divided by the correct thing. Okay, so thank you very much. Uh, for so 479 divided by 91. That's that's still not going to be a nice number. Let me check if I made any other mistake. Yeah, it is 91. Thank you. Uh, and so 479 over 91. I would have made a big mistake there. 479 over 91. Hmm. Still doesn't come out to a nice number, does it? Unfortunately. And so I get that the sum of the first n terms is just n over 2 times 2a1 plus n minus 1d. A1 was 5. And d is 479 over 91. None of that's going to be very nice, is it? And so the sum of the first n terms is 10 plus 479n over 91 minus 479 over 91 and over 2 multiply and divide by 91. So that's 9, 10. Okay, so they'll still look relatively horrible. And so this is equal to 479 over 91n plus 910 minus 479, 431 over 91. I guess let's factor out the 479 over 91. So this is equal to n times 479n plus 431 over 2 times 91, 182. Not such a nice formula. Oh well, and that is the formula to find the sum of the first in terms, and that's never going. Oh, okay. Oh, I wonder if my eyes are bad. Of course, my eyes are bad. It was 18, not 14. Oh, I hate you. It was 18. There were 18 terms, not 14 terms. So this is 39 with bad eyes. So it was not 30. It goes 39 would have been a better answer because it was supposed to be the sum of the first 18 terms, not the first 14 terms. That's why it did not come out to a nice formula. Okay. Oh well, we derived a formula, even though it wasn't the nicest formula. But the technique is correct, even though, well, the technique is correct and the answer is correct for the problem as stated. But obviously, I gave you a nicer problem in the book as compared to what I just tried to accomplish. Any questions about this? Okay. So we have the following facts um, for series. And so first is the sum, let's say k equal 1 to n of 1 is equal to n. So if you add up 1 n times, you get n. 2, the sum k equaling 1 to n of k is equal to n plus 1 over 2. 3. The sum k equaling k sub 0 n ak plus the sum k equaling k0 to n bk equals the sum k equaling k sub 0 n ak plus bk. Next, sum k equaling k0 to n c a sub k is equal to c times the sum k equaling k sub 0 to n of a sub k. So you can distribute out a common factor. It's a distributive property. So let's, and maybe one last one. Sum k equal 1 to n k squared is equal to, did I show that? Ah, there it is. Is equal to n 2n plus 1 over 6. Okay? So, let me show some of these. So let me show that if you add up n terms, if you add up 1 n times, you get n. Okay, so let's prove this by induction. So let's do the initial case. So the sum k equaling 1 to 1 of n of 1 is this equal to 1. So thus the sum k equaling 1 to n of 1 is equal to n when n equals 1. Okay, so good, that's shown. So now let's do the induction step. Well, let's suppose that the sum k equaling 1 to n of 1 is equal to n. Then we want to show that the sum k equaling 1 to n plus 1, I want to show that that's equal to n plus 1. Well, this is equal to the sum k equaling 1 to n of 1 plus the very last term, which is 1, which is equal to, well, the sum of k equaling 1 to n is just equal to n, so therefore it's equal to n plus 1. So thus, we have shown the deduction step, that if the formula is true for n, then this implies that it is true for n plus 1. Therefore, by the principle of mathematical induction, summation k equal 1 to n of 1 is equal to n for all natural numbers n. And so I am done. Okay. I guess let me show 2. Oh, so 2 actually is just a special case of where a sub 0, a sub 1 is 1, and the common difference is 1. So I mean, that could be, so we've actually already shown that. So okay, so, well, we have that. This, we've already shown this. The sum k equaling 1 to n of a1 plus k minus 1d is equal to n over 2, 2a1 plus n minus 1d. So we've already shown that. And now, or actually, let's see. We actually know, let's do it this way. Let's do it with the first and last term, because that's also true, is equal to a1 plus an. Okay, well, so therefore, in this case, A1 is 1. So the sum k equaling 1 to n of k, that's the same as the sum k equaling 1 to n of 1 plus k minus 1 times 1. Because, well, k minus 1 plus 1 just gives you k. And so in this case, A1 is 1 and AN is n, which is what we wanted to show. Done. Okay. And so that's that. And I guess 3 and 4 are actually problems. So maybe we'll do that. Those are problems in the book. So uh, maybe I'll do problem like 48. Actually, well, yeah, so that's problem 48 in the book. So let me do problem 48, which is actually to show one of these. And so let me do that. Use mathematical induction to show that for every natural number k sub 0 and for every non-zero natural number c and for every natural number n with n greater than k sub 0, we have the following. Sum k equaling k sub 0 to n of c a k equals c sum k equaling k0 to n of a sub k. So I want to show this. And so let's use, again, mathematical induction to show this. So let's do the initial case. The initial case in this case is when k is k sub 0. And so let's show this for k sub 0. And so I'm going to show that if I replace n by k sub 0, that this formula works. Well, plug in k sub 0, so you get a k sub 0. So therefore, so thus, we have shown that the sum k equaling k sub 0 n c a sub k is equal to c, the sum. Well, maybe I should have written one little step in here. C a sub k0 which is equal to c sum k equaling k sub 0 ak. Thus, we have shown that these are equal when n is equal to k sub 0. So that was the initial case. So now let's do the induction step. So the induction step is to show that if we assume that this is true for n, then that implies that this formula is true for the case when n is replaced by n plus 1. And so, let's assume that this formula holds. Oops. That this formula holds for n. Then let's look at what happens for n plus 1. And so for the first n, let's add these up. For the last one, well, the last one is c a sub n plus 1. Okay, and so this is equal to, or I can factor out the c out in front of the summation. And now I can factor out the c from each of these terms, since the c is in common. But this last term here is just the next term in this summation. And so this is just the sum, k equaling k0 to n plus 1 a sub k. And so I've shown the induction step. So therefore, by the principle of mathematical induction, for n being a natural number, we have that the sum k equaling k sub 0 n c a k equals c sum a sub k, k equaling k0 to n. Okay, good. And so I'm done. Okay, and the other ones obviously are going to be very similar. So let me do, let's say problem number, so that was 40. How about 41? Let me do problem number 41. The sum, k equaling 1 to n of 2k is equal to n plus 1. Okay, so let's do that. And let's see, did we do, no, we did, I don't think we did that one. That would have, oh, I see, we did, I think we did 25, which was the corresponding, which is the corresponding formula, but we only did it for the first 100 terms. Okay, so let's show this. Well, note the following. So we could actually derive this formula. So note that this is the same as the sum k equaling 1 to n of 2k. By the very last thing that we proved, this is just 2, the sum k equaling 1 to n of k. But by the previous thing that we had proven, this, we have, we didn't prove that. Yeah, we did derive, we did show that. We just didn't prove by mathematical induction. We have that this is equal to n over 2 times n plus 1. So the 2's cancel, and so you get n plus 1, which is the formula. Now, of course, they didn't want us to do it that way. They wanted us to use mathematical induction. So let's use mathematical induction to show this. And so we have here that, well, let's do the initial case. So I have the sum k equaling 1 to 1 of 2k. So that's equal to 2 times 1, which is 2. And now let's look at the case when we place n here by 1. So 1 times 1 plus 1 is 1 times 2, which again is 2. So these are both equal. So therefore, I've shown that the sum k equaling 1 to n of 2k equals n times n plus 1 when n is equal to 1. So that's what I've shown. So I've shown that this formula works here when n is 1. Now let's do the induction step. And so let's assume that this formula works for the first n terms. And we want to show that if I replace n here by n plus 1, then this formula will work. So maybe I'll put in parentheses. I want to show that the sum k equaling 1 to n plus 1 of 2k is equal to, replace n here by n plus 1, replace n here by n plus 1. So this is the formula I want to show. So I want to show that assuming this very first step, I can show the very second step. So let us add the first n plus 1 of these. As usual, what I'll do is I'll just add the first n of these, and then I'll explicitly evaluate the very last term. And then simplify to write it in the form that we want. Okay, so this is equal to the sum of the first n terms plus the last term. The last term is found by just replacing k by n plus 1. Okay, so this is equal to, well, they told us it was equal to n plus 1 plus 2n plus 1. Let's factor out what's in common, n plus 1. What remains is n plus 2. But note, I just want n plus 1 plus 1. So I can write 2 as 1 plus 1. And so I have written this in the form that I want. And so therefore, I've shown that the induction step works. So therefore, by the principle of mathematical induction, for all natural numbers n, the sum k equaling 1 to n of 2k is just equal to n times n plus 1. And that's what I wanted to show. Okay. Let me do, so 42, 44, 46. Okay. 42, 44, 46. So how about 45? Yeah, so let's show 45. Sum k equaling 1 to n of 10k minus 6. I want to show by mathematical induction that this is equal to n times 5n minus 1. Okay, so let's show that. So let's first do the initial case. So let's do the case when n is equal to 1. And so so let's replace n here by 1. Oh, okay. Sorry. I hope I didn't. Here, I've got to check if I lost connections and everything else. Okay, here, wait. Okay, there's no class on Monday, no. Can everyone still see me and hear me? Yes, you can hear me and see the right in the background? Yes, kind. Okay, good. Okay, good. Okay, so the cord fell out and a few other things happened. Okay, so let's do the initial case. So let's replace n here by 1. So this is equal to 10 times 1 minus 6. That's that's the only term. And so 10 minus 6 is 4. Next, let's see if the formula works for this case. So let's replace n here by 1. So 5 times 1 minus 1. So that's 1 times 5 minus 1, which is 4. Good, so they both are the same. So so we've shown that the sum k equaling 1 to n of 10k minus 6 is equal to n times 5n minus 1 when n equals 1. Okay, so let's do the induction step. And so, let me suppose that the sum k equaling 1 to n of 10k minus 6 is equal to n times 5n minus 1. I want to show, so at the end, what I want to show is that when I replace n here by n plus 1, the formula is the same where I replace n by n plus 1. So this is what I want to show. And let's see if it works. And so I have that the sum k equaling 1 to n plus 1 of 10k, 10k minus 6, that's equal to, well, just add up the first n terms and then plug in the last term, which is 10 n plus 1 minus 6. Well, this is equal to, by the assumption, n times 5n minus 1. This last term is, well, let's see, let's multiply the 10 inside the parentheses. 10n, oops, this is equal to 10n plus 10 minus 6. Let me multiply the n inside the parentheses. So I get 5n squared minus n plus 10n plus 4. So this becomes 5n squared plus 9n plus 4. Let's factor this. This factors as n plus 1 times 5n plus 4. Okay, so if I check, I get 5n squared plus 4n plus 5n is 9n plus 4. And so this is, again, just one of your, polynomial factoring of quadratics. So let's simplify this. Let's write this as n plus 1. Now, remember, this is my goal. And so my goal is to write this as 5n plus 5. Well, 4 is 5 minus 1. So now I can group the 5n plus 5 minus 1. So notice that I wanted a minus 1 here. But now I can factor out a 5. From this term that I put a parenthesis around. And now if I look, that's exactly what I wanted. N plus 1, 5n plus 1 minus 1. And so that means